5 houses, 15 clues. The word zebra never even appears. Yet there's only one answer. Let's start with a puzzle you've probably run into at least once. You've seen puzzles like this. You're handed bite-sized clues like coffee is drunk in the greenhouse. And at the very end it asks, so who owns the zebra? This puzzle almost always comes with the same tagline attached. That's why it's commonly called Einstein's riddle. But let me tell you one thing up front. Those two claims are both false. The truth is actually more interesting. This isn't the private preserve of a genius. It belongs to anyone who refuses to give up. Inside that solution lies, whole and complete, computer science's most elegant way of battling a staggering number of possibilities. That's why it stayed a fixture of programming textbooks for over 60 years, and in 2025 it was summoned again as a test for cutting-edge AI. Alright, let's set the stage first. We'll work with the original version that first surfaced in 1962, titled exactly that. Who owns the zebra? 5 houses stand in a row left to right. Each house comes with 5 attributes, one of each. The house's color, the resident's nationality, their drink, their cigarette, and their pet, 5 categories in all. The rules are simple. Within each category, the 5 values differ from house to house. Exactly one house is red. Exactly one house drinks coffee. Our job is to work out exactly what belongs in which house, using nothing but the 15 clues below. Let's run through the clues. Here are the first 8. And here are the remaining 7. And there are 2 final questions. Who drinks water? Who owns the zebra? The mischievous trap. Nowhere in the 15 clues do water or zebra appear. The 2 show themselves only as the empty cells left once everything else is filled in. So how do you solve this puzzle by hand? The secret is toppling the first domino. The most common mistake with a puzzle like this is trying to hold it all in your head and losing your way. There's a better way. Start by nailing the absolutely certain clues down on paper. The most certain clues are the ones that pin down an exact spot. I spot 2 of them. The moment you nail down these 2 cells, the dominoes begin to fall. Clue 15 says the Norwegian lives next to the blue house. The Norwegian is in house 1, and its only neighbor is house 2. So house 2 is blue. So what color is house 1? Blue is already house 2, and green sits just right of ivory, so it can't be at the far left. If it were red, the Englishman would have to live there. But house 1 is the Norwegian's. If it were ivory, house 2 would have to be green, but house 2 is blue. Cross them off one by one and a single answer remains. House 1 is yellow. And clue 8 says cool is smoked in the yellow house, so house 1 smokes cool. See that? All we did was pull on 2 position clues, and a whole house's color, and even its cigarette, fell into place one after another. This is what the puzzle really is. Less a matter of difficulty than a game of persistence, starting from certainty and narrowing it down one cell at a time. Fill it in to the end and you'll realize, the arrangement the clues point to is the only one there is. But a question arises. With this much freedom, is there really only one answer? Just how many arrangements are even possible? Let's count the possibilities. In this haystack, we're hunting for a single needle. Take just the colors. The number of ways to line up 5 colors across 5 houses is 5 factorial. That is 120. Nationality is 122, and so are drink, cigarette, and pet. The 5 categories are settled independently of one another. So the total number of possible arrangements is 120 to the 5th power, 5 factorial multiplied 5 times over. About 24.9 billion. In this vast haystack, exactly one needle satisfies all 15 clues. I set a computer loose to find it directly. It builds the permutations one by one, discarding any arrangement that breaks a clue on the spot. Each time we apply another batch of clues, counting how many arrangements are still alive gives this. Graph this staircase and you get a funnel of shrinking possibilities. The vertical axis is a log scale, so every step down cuts the count tenfold. Starting from about 24.9 billion at the far left, the possibilities plunge like a cliff with each added clue and settle onto a single one at the far right. Here's something worth stressing. Saying there are 24.9 billion possibilities does not mean it's hard. Reason cleverly and this number shrinks dramatically. Pin 1 category's ordering as your reference, and one factor of 120 drops out of the product. And if you narrow things by ruling out that's impossible, the way we did by hand, the cases you actually inspect are far fewer. The funnel above is the proof. So how exactly does a computer do this pruning? To a computer, this puzzle is a very familiar guest. Its name is the constraint satisfaction problem, CSP for short. Sounds grand, but the idea is simple. When you have blanks to fill and rules those blanks must obey, it's the problem of finding a filling that satisfies every rule. In our puzzle, the blanks are each house's 5 attributes, and the rules are exactly those 15 clues. The clues fall into 3 types by their nature. Of these, position clues are the most powerful because they nail a blank down in one stroke. That's exactly why we started there. The most basic way a computer finds the answer is backtracking, retracing your steps. Picture finding your way through a maze. At a fork, you try one path first. When you hit a dead-end wall, that is, a clue violation, you return to the last fork and try a different path. The key is this. The sooner you hit a wall, the more of the countless paths beyond it you skip in one go. So, for all that the number is 24.9 billion, the answer actually pops out in the blink of an eye. Add a touch of finesse and you get constraint propagation. Each time you lock in a clue, you spread its ripple to the other blanks, narrowing their candidates ahead of time. That domino we set off, going straight from Norwegian is house 1 to house 2 is blue, is exactly the feel of constraint propagation. And recall what we did back in part 2. We reached first for the cells with only one candidate, the position clues. That instinct has a proper name too. In computer science it's called the MRV heuristic, the minimum remaining values principle. That way, before you plunge deep down a wrong path, you meet a dead-end wall early and finish the search sooner. That move people make so naturally turns out to be exactly the optimization technique a solver deliberately uses to squeeze out speed. All of this works because the clues are really a dense web of relationships. Let's spread that web out into a single picture. The blue solid lines are items tied to the same house. The orange dashed lines are next to or immediately right of relationships. The purple tags mark the 2 items with fixed positions. The Norwegian in house 1, milk in house 3. Pull any one knot of this web and a tremor spreads along the threads, so that all 25 knots converge into one. Because the clues transcribe almost verbatim into computer rules, the zebra puzzle has long been cherished as a textbook example for declarative languages like Prolog. In fact, from Russell and Norvik's AI textbook to solution collections in dozens of languages, this puzzle turns up without fail. Now it's time for the finale. That one and only arrangement reveals the true identities of water and zebra. Here is the one arrangement the solver found, laid out at a glance with each cell tinted by its house color. Let's read from the left. In house 1, the yellow house, the Norwegian drinks water, smokes cool and keeps a fox. In house 2, blue, the Ukrainian drinks tea. In house 3, red, the Englishman drinks milk. In house 4, ivory, the Spaniard keeps a dog. In house 5, green, the Japanese drinks coffee. And it's that very house where the zebra is kept. The 2 guests who stayed hidden to the very end reveal themselves in the leftover spots. Water belongs to the Norwegian, and the zebra's owner is the Japanese. If you've made it this far, you've just finished by hand the very puzzle that supposedly only the top 2% can solve. But is it really Einstein's puzzle? Now for the story I promised. To cut straight to it, Einstein did not create this puzzle. There's no evidence anywhere that Einstein made it. A rumor that Lewis Carroll made it floats around too, but that one has no basis either. The most reliably documented source isn't a genius's desk, it's a single magazine. It ran in the December 17, 1962 issue of Life International, under the title Who Owns the Zebra? With no author's name. The following March, alongside the answer, it reportedly ran the names of hundreds of readers worldwide who had solved it. That one fact alone, that hundreds of people got it right, shows how flimsy the claim only 2% can solve it really is. The decisive alibi is hidden inside the clues, the ages of the cigarette brands. Cool didn't appear until 1933, Parliament until 1931, and Old Gold until 1926, all products of the 20th century. But Carroll died in 1898, Einstein's childhood was back in the 1880s and 90s, and even he passed away in 1955. There's no way two men who lived long before could have written a puzzle that plainly names a brand which didn't exist until 1933. The 2% can solve it line is likewise a rumor with no source. Here's the truth. This isn't a hard puzzle. It's a puzzle of persistence. It's not that most people can't solve it, they just quit partway through. What's fun is what came next. Far from growing old, this 60-year-old magazine puzzle keeps living on, moving from stage to stage. A variant that swaps only the nationalities and brands to ask, who owns the fish? Whose answer is the German, has even eclipsed the original in fame. And in 2025, researchers tested cutting-edge AI on 1,000 puzzles from this family, the Zebra Logic study. The results were telling. Once the number of possibilities crossed a certain threshold, even the top-performing models saw their accuracy collapse. And it wasn't the kind of wall you break through just by making the model bigger. Why? The solver we wrote in Python spells out its state, the grid, clearly, and when it gets stuck, it retraces and fixes it, symbolic reasoning. Today's large language models, by contrast, are essentially machines that stitch on the next word by probability. So they're weak in working memory. The way a person draws a table on paper, carefully jotting down the mid-solution state and revising it. So the moment the backtracking runs deep, they appear to buckle structurally, faced with a problem a person could finish given nothing but time. So the next time someone hands you this puzzle as Einstein's problem, feel free to answer with a knowing smile. That it's neither Einstein's nor the 2%'s, it belongs to everyone who followed the clues all the way to the end. If today's story intrigued you, subscribe, like, and turn on notifications, and I'll see you in the next Odyssey.